System design pattern simplified. System design can feel overwhelming, but what if I told you that most complex distributed systems are built using just a handful of proven patterns? Today, we're breaking down 12 essential system design patterns that every developer should understand. These aren't just theoretical concepts. They're the building blocks powering the applications you use every day. Introduction. Whether you're preparing for a system design interview, architecting a new application, or trying to understand how large-scale systems work, these patterns are your foundation. Each pattern solves a specific problem that occurs when building distributed systems at scale. Let's dive in and see how these patterns work in the real world. Pattern 1. Circuit breaker. First up is the circuit breaker pattern. Think of it like the electrical fuse box in your house. When a service starts failing repeatedly, the circuit breaker trips and stops calling that failing service temporarily. This prevents cascading failures from bringing down your entire system. Netflix famously uses this pattern in their API handling. When a recommendation service fails, instead of waiting for timeouts and potentially crashing the entire Netflix experience, the circuit breaker kicks in, and the app continues working. You just might not see personalized recommendations for a few minutes. The circuit breaker monitors the service and automatically closes again when the service recovers, restoring full functionality. Pattern 2. Rate limiter. The rate limiter pattern is like having a bouncer at a club. It controls how many requests a user or service can make within a specific time window. This prevents system overload and ensures fair usage. Think about toll booths on a bridge. Even if there's a traffic jam, only a certain number of cars can pass through each booth per minute. API gateways use rate limiting extensively. Twitter, for example, limits how many tweets you can post per hour, and their API limits how many requests third-party applications can make. This protects their infrastructure from being overwhelmed while ensuring all users get fair access to the service. Pattern 3. Bulkhead. The bulkhead pattern takes its name from ship design, those watertight compartments that prevent the entire ship from sinking if one section is breached. In system design, it means isolating different parts of your system so a failure in one area doesn't affect the rest. Consider how cruise ships have separate compartments for different functions. If the engine room floods, the dining areas and passenger cabins remain safe. Similarly, in microservices architecture, you might isolate your payment processing service from your user authentication service. If authentication goes down, users can still complete purchases using existing sessions. Pattern 4. Retry pattern. The retry pattern is exactly what it sounds like. When a request fails, try again with some intelligent logic. But it's not just about blindly retrying. It's about doing it smartly with delays and limits. Imagine trying to call someone whose phone is busy. You don't immediately redial, you wait a moment and try again. HTTP clients use this pattern extensively. When a network request fails due to a temporary glitch, the client might retry with exponential backoff, waiting 1 second, then 2, then 4, and so on. This gives the failing service time to recover while not overwhelming it with retry requests. Pattern 5. Timeout pattern. The timeout pattern prevents your system from waiting indefinitely for a response. It's like hanging up a call if nobody answers within 30 seconds. You don't wait forever. In network communications, this is crucial. Without timeouts, a single slow service could cause your entire application to hang. Web browsers implement timeouts on every request. If a web page doesn't load within a reasonable time, the browser stops waiting and shows an error. This keeps the user experience responsive, even when some services are slow or unresponsive. Cache aside pattern. Cache aside, also known as lazy loading, is like checking your fridge before going to the grocery store. You only fetch data when you need it, and you store it locally for quick access next time. This pattern is everywhere in modern applications. When you visit a website, your browser checks its cache first. If the resource isn't there, it fetches it from the server and stores it locally. Redis databases commonly implement this pattern. Applications check the cache first and only query the main database if the data isn't cached. This dramatically reduces database load and improves response times. Write-through cache. Write-through cache is like keeping both your diary and a sticky note updated simultaneously. When you write data, it goes to both the cache and the database at the same time, ensuring consistency. This pattern ensures that your cache and database are always in sync, but it comes with a performance cost since every write operation has to happen twice. Banking applications often use this pattern because data consistency is more important than write performance. When you transfer money, the transaction is written to both the cache and the permanent database simultaneously, ensuring no discrepancies. Publish-subscribe. The publish-subscribe pattern is like a radio station broadcasting to multiple listeners. One service, the publisher, sends messages, and multiple other services, the subscribers, can listen and react to those messages. Radio broadcasting is the perfect analogy. The radio station doesn't know who's listening, and listeners don't directly communicate with the station. Apache Kafka implements this pattern beautifully. When a user makes a purchase, the order service publishes an event. The inventory service, email service, and analytics service all subscribe to this event and handle their respective tasks independently. Event sourcing. Event sourcing is like keeping a detailed journal of every financial transaction instead of just tracking your current balance. Instead of storing the current state, you store every event that led to that state. In financial systems, this is incredibly valuable. Instead of just knowing you have $1,000 in your account, the system stores every deposit, withdrawal, and transfer that led to that balance. This provides complete audit trails and allows you to reconstruct the state at any point in time. Git version control works similarly. It stores every change, commit, rather than just the current state of your code. CQRS, Command Query Responsibility Segregation. CQRS separates read and write operations into different models, like having separate cashiers for sales and returns at a store. This allows you to optimize each operation independently. Think of a busy restaurant, where one person takes orders, writes, and another person serves food, reads. Each role is optimized for their specific task. In software, you might have a write database optimized for transactions and a separate read database optimized for queries. This is especially powerful in e-commerce systems where you have many more product views, reads, than purchases. Strangler fig. The strangler fig pattern is named after a plant that gradually grows around and eventually replaces its host tree. In system design, it's a strategy for gradually replacing a legacy system without a complete rewrite. Imagine renovating a house while living in it. You replace one room at a time rather than tearing down the whole house. Companies use this pattern to modernize legacy systems. They gradually route traffic from the old system to new microservices, one feature at a time. Eventually, the old system is completely replaced, but the transition happens smoothly without disrupting users. Saga pattern. The Saga pattern manages distributed transactions by breaking them into smaller, local transactions with compensation actions. It's like booking a complete vacation. If one part fails, you need to cancel everything else. When booking a trip, you might reserve a flight, hotel, and rental car. If the hotel booking fails, you need to cancel the flight and car reservations. The Saga pattern handles this by defining compensation actions for each step. In distributed systems, this might involve multiple services. If a payment fails after inventory is reserved, the Saga automatically releases the inventory and notifies the user, maintaining system consistency across services. Conclusion. These 12 patterns form the foundation of modern distributed systems. They're not just academic concepts. They're battle-tested solutions used by companies like Netflix, Amazon, Google, and thousands of others to build reliable, scalable applications. The key insight is that you don't need to invent new solutions for common problems. These patterns provide proven approaches that you can combine and adapt to solve complex system design challenges. Each pattern addresses specific concerns: reliability, scalability, performance, or maintainability. As you design systems, think about which patterns apply to your specific challenges. Are you dealing with unreliable services? Consider circuit breaker and retry patterns. Need to handle high traffic? Look at rate limiter and caching patterns. Building a complex workflow? Saga and event sourcing might be your answer. Remember, the best system designs often combine multiple patterns. Netflix doesn't just use circuit breaker. They combine it with rate limiting, caching, and publish-subscribe patterns to create a resilient, scalable streaming platform. Closing question. Which of these patterns have you encountered in your projects? And more importantly, which ones do you think would solve current challenges in your systems? Understanding these patterns is just the beginning. The real value comes from knowing when and how to apply them in your specific context.